Imagine a safe that follows an unusual rule. It will only open if two different people insert their keys and turn them at exactly the same time. One key alone accomplishes nothing. The mechanism ignores every attempt made by a single person. But the moment both keys are turned together, something hidden inside the safe changes instantly. Quantum computing has its own version of this mechanism. It is called the Toffoli Gate. The Toffoli Gate contains 2 control qubits and 1 target qubit. The rule is surprisingly simple. The target qubit changes only when both control qubits are equal to 1. One control being active is still not enough. Even when the other control is turned on, the target remains untouched. Only when both controls become 1 does the target finally change. If the target was already 1, it flips back to 0. Out of 8 possible combinations, only 2 are affected by the Toffoli Gate. Unlike ordinary logic gates, the Toffoli Gate never destroys information. This property makes it important in reversible computing, where information can theoretically be processed without wasting energy. Surprisingly, classical logic gates like AND can be constructed using the Toffoli Gate. It behaves almost like a universal toolbox for reversible computation. Quantum mechanics allows something even more remarkable. The control qubits can exist in multiple possibilities simultaneously.
The Toffoli Gate acts on every branch of the superposition at the same time. This creates intricate relationships among 3 quantum systems.
Toffoli gates play an important role in quantum error correction protocols. They are also used to build quantum adders, multipliers, and arithmetic circuits. Sophisticated algorithms for factoring large numbers rely heavily on operations built from Toffoli gates. Performing a high-quality Toffoli gate on real hardware remains an engineering challenge.
Unlike CCNOT, which connects 2 qubits, the Toffoli Gate coordinates the motion of 3.
The Toffoli Gate is essentially a quantum permission slip. 2 approvals are needed before action is allowed. The mysterious safe was never about protecting valuables. It was teaching us how quantum computers make decisions. Every action taken by the Toffoli Gate can always be reversed, preserving information at every step. The Toffoli Gate teaches quantum computers an important lesson. Sometimes, one decision should only happen when multiple conditions agree. By combining gates like Hadamard, CCNOT, and Toffoli, quantum engineers construct increasingly sophisticated machines capable of remarkable computations. In quantum computing, power does not come merely from changing information. It comes from learning when information should change and when it should remain exactly as it is. The Toffoli Gate is more than just another quantum operation. It stands as a bridge between classical logic and quantum mechanics, preserving information